going to tell you a little bit about nanoscience, just as kind of a motivation, and then explain a little bit at a kind of qualitative level of the tool that we use to study the nanoscale, which is called the scanning telling microscope. And I'll give one example of our research, which is looking at magnetic impurities in semiconductors. And then I hope actually to show you how we're remote controlling the microscope, which has been very helpful during the COVID shutdown because the occupancy in the lab is limited. And so I think this is something I'm excited about just in terms of being able to do experiments even from home. Okay, so before I forget, I just wanted to thank the group. So this is a current list of the students in the group. There's actually 7 PhD students now, ranging from grizzled 4th and 5th years to fresh 0th years, or first years now, I guess. And I usually do have actually 2 or 3 undergrads working in the group. And I'll apologize in advance if some of you have sent me emails and I've ignored them. It hasn't been with malicious intent, but it turns out that, as you might have heard, if any of you were trying to do summer research, they basically were asking undergrads to only do remote research. And so I just was having a hard time figuring out maybe how, what kind of different projects people could contribute to remotely. And so the only undergrad currently working in the group is Matt, who's been doing some simulations of magnetism remotely. And so, but I hope that as things open back up, I've heard at least that there's plans to phase in-person undergrad research in the not too distant future. Okay, so just for a sense of scale, I like to show this because it kind of shows what the nanometer scale is in addition to things that we might be more familiar with, such as the macro scale. And so this is a guy that's passed out on a picnic blanket. Look, he's been reading Science magazine, so that's probably why he's asleep. So if you zoom in on the left by 1 order of magnitude and zoom out on the right by 1 order of magnitude, so we have 10 to the minus 1 meters, so zooming in on the man's hand, and zooming out, you can kind of see that he's on a picnic blanket in the middle of the park. And if you keep going, so kind of see wrinkles in the man's hand on the left. On the right, that this park is Golden Gate Park in San Francisco. As you keep going, so this is the cellular level on the left and kind of the satellite level on the right. Now at 10 to the minus 7 meters, we start to see that cells are made out of DNA and proteins. And on the right, there's the orbit of the moon, so that's 10 to the 9 meters. On the left is the nanometer scale, so 10 to the minus 9 meters. So roughly 10 to the minus 9 meters is about the size of an atom. So in particular, for example, hydrogen, which you might have encountered if you're taking intro quantum mechanics. So the hydrogen atom is about half a nanometer in size. Okay, so the nanometer scale is kind of the scale of atoms. And atoms, of course, make up molecules. Surprisingly, it turns out that there's just about as many orders of magnitude going small as there is going large in the universe. And perhaps coincidentally, the human scale is almost kind of in between. Okay, so I wanted to start with just some motivations for kind of this broad field that we call nanoscience. And obviously, sustainability is one of our society's kind of pressing challenges going forward. And I want to give this kind of nice example that makes use of nanoscience. It's called the artificial leaf. This is a very broad and active area of research. I think Dan Nocera's group at MIT is perhaps the best at popularizing it. So if I click on here, hopefully it'll switch over to my browser window. So this is it's called an artificial leaf. And please let me know, someone break in if they can't see the browser window. So what this video is showing is there's a strip of a catalyst material that's white. And the strip of material is immersed in water. And if you look closely, you can see these little bubbles that are forming. So it turns out what's actually happening is that there's, this is called electrocatalytic splitting of water. And so what's happening is that, or actually this is photocatalytic splitting of water. So you have light that's illuminating this strip of material. that's causing, so it's splitting the water up into hydrogen and oxygen. And those bubbles are H2 and O2 that are coming off of the surface. If you design this catalyst right, you can produce oxygen on one side of the strip and hydrogen on the other side of the strip. And so you can imagine inserting this material in a fuel cell, for example. And so you'll generate the raw materials of the fuel cell just by having water and light. So it turns out if you look, if you zoom into the surface of the artificial leaf and you want to study some of the kind of fundamental chemistry, that happens at the nanometer scale. And so what I'm showing here are scanning telling microscope images, and I'll explain a little bit how those work in just a moment. These are images of the components of water. So these faint red blobs here are individual hydrogen atoms, and these kind of orangey blobs are individual OH groups. And so if you take an H and an OH and you have the right surface, you can produce water, H2O. And so this is actually a movie of these kind of images. So just for reference, so these are individual molecules. So this image square is about probably 5 nanometers or so, 5 nanometers square. So if I run this movie, this is just taking a snapshot of these pictures over and over again. You can actually see that all the blocks except for these ones marked with circles, these are actually defects in the catalyst material. So this particular surface is titanium dioxide, which is one of the more well-studied surfaces for this kind of water splitting. And if you look at a larger scale, you can kind of compile similar movies. So if you think about all the steps that have to go into this splitting water process, you need to take water, it needs to split apart into hydrogen and hydroxyl groups, and perhaps ideally oxygen. And then the oxygens to combine to get O2, and it needs to combine to get H2. And so there's a lot of nanoscience that goes into understanding these catalyst surfaces such that you take H2O and preferentially make H2 and O2. And so studying kind of the influence of these defects, for example, is a major trend in nanoscience to understand how chemistry happens at these defect sites. Okay, so that's kind of a sustainability type motivation. Of course, so what I showed you is that it works, but the reason that we're not driving fuel cell powered vehicles is that there's a lot of science that has to happen to get something that works, in a 1-inch size strip in the lab to, something that can work at large scale that could actually address our society's needs. Okay, so the second example I wanted to mention was computing or electronic devices. So most of you have probably heard of Moore's Law, which is this kind of self-fulfilling prophecy made by one of the founders of Intel. And basically the idea is that computers have gotten faster over the years by continuously miniaturizing the transistor. And it turns out actually now that transistors have gotten small enough that the fact that the semiconductors that they're made out of, those semiconductors are not perfect materials, they have some defects. And in particular, the distribution of those defects and the number of them start to really impact the performance of transistors. And so what I'm showing in this panel here is a simulation showing a channel in a transistor, and these kind of splotches here are individual point defects or atomic impurities in the semiconductor material. And in the scatter plot is shown kind of how the performance, called the threshold voltage for the transistor in the y-axis. So how does that depend on number of impurities or number of these little splotches in the material? And this scatter kind of shows you that, you make 10 to the 9 of these transistors in a computer chip, and you're going to get some spread in those because the number of impurities is going to vary statistically. So this plot that I'm showing on the right here is already far out of date. I have tried to look for an updated version, but haven't so far been successful. But this shows the technology node. I think right now we're in something like the 10 to 7 nanometer technology node. If you kind of look at the average number of these kind of splotches, these impurities, that corresponds to about 10. So if you think about this in a statistical fashion, you might expect to get Poisson statistics because these impurities are random. And so for Poisson statistics, which you might have learned in the sophomore lab course, you expect square root of n type fluctuations. And so if you have 1 million impurities, square root of 1 million is a big number, but it's still a small percentage compared to 1 million. Whereas if you have 10, then square root of 10 is 3, and so that's 30% of the number. And that's what produces this really wide spread in the performance of these transistors, because now there's so few impurities that just the random fluctuations in that number can have a big impact. Okay, so that's the motivation. And let me just pause here to see if anyone has a question or comment that they'd like to make at this point. And yeah, either Nathan, if you can monitor the chat window, or feel free to unmute yourself also. Okay. So I want to tell you at kind of a fun level, kind of how the tool that we use to study the nanoscale. So it's called the scanning tunneling microscope. And so just at a qualitative level, let's unpack what we mean by tunneling. So tunneling is quantum tunneling, which is one of these weird aspects of quantum mechanics, which is that, and one way to think of it is that at the length scales where quantum mechanics is important, objects are no longer sharply defined. So you have an uncertainty principle related to their position and momentum. And you can kind of think of an object as not having really sharp edges. So in particular, when quantum mechanics is important, things are fuzzier. And that fuzziness can lead to some dramatic effects called tunneling. So in particular, imagine that you had so this is a kind of a picture of a barrier. So you have a barrier between a lion and a person. So if the barrier is too high for the lion to jump over, then in classical physics, the person is safe. So the lion can never reach the person and attack him. In quantum mechanics, however, because in principle, the lion is no longer just a sharply defined object, but has some fuzziness to it, some of that fuzziness actually leaks through this barrier. So you might think of that as like a wall or a fence at the zoo. And by chance, essentially the environment might measure the position of this lion, and it's what we call its wave function will suddenly snap to the right side of the barrier. And now the lion and the person are on the same side. And if the lion's hungry, the lion might chase the person. So fortunately, the fuzziness of lions and macroscopic objects is extremely small. It's on the order of 10 to the minus 30 meters. And so this spreading out through the barrier is negligible for any kind of macroscopic object like a lion. It turns out, and so at the zoo, you're likely to be safe, although statistically there's a probability that the lion will kind of spontaneously snap onto the other side of the fence, and that probably takes well beyond the age of the universe for that to happen once, but it could happen. Okay, so but for electrons, this quantum tunneling process is very important because electrons are tiny, and so I envision the scanning tunneling microscope like a record player. I think people still remember what a record player is. The notion is that you have a stylus needle, and in a record player, you scan the record, you kind of rotate the record, which scans it across this needle, and the needle deflects due to grooves in the record. The music is encoded in terms of the bumpiness of the record. Okay, so if you zoomed in to the end of this needle, at the atomic scale, you would find some fraction of the time that there's some blob of atoms that sticks out more than all the others. And if you bring this blob of atoms within a very close distance to, let's say, a conducting surface, so let's say, it turns out that the electrons in the blob of atoms can quantum mechanically tunnel into the surface. So what we do in the microscope is we hook up a battery between this needle and the surface. And you could use like a AA battery for this if you wanted to. When the tip is far away, so far, there's going to be zero current because the electrons can't tunnel across this barrier. which is vacuum. So this needle is kind of hovering over a surface that we want to study, and this is happening in vacuum, although actually, surprisingly, this can work also in air or even liquids. When we bring this needle close to within about a nanometer and we have this bias voltage hooked up, then some fraction of the electrons can quantum mechanically tunnel. And so that produces a current which we can measure. Okay, so it turns out that this current is exponentially sensitive to the separation between the needle and the surface, because quantum mechanical tunneling goes as the exponent of the width of the barrier. And so in the case of STM, if I, instead of 1 nanometer, if I go to 1.1 nanometers, the current will actually change by a factor of 10. Because it's easy to measure factors of 10 changes in current, it's a very high resolution microscope technique. The way we make images is that we basically raster this needle across the surface, kind of like the process of the record player. Oh, sorry. And what we do is we move the needle up and down in order to maintain a constant tunneling current. And so the image we actually display is the trajectory of the tip as it's scanning across the surface. So atoms happen to have electrons, and as often as not, that means that there's a high probability for tunneling. So if you have a high probability for tunneling, that means you can back the tip a tiny bit away and still maintain a constant current. And so over atoms, like in a surface, like I'm showing here, the tip moves back a little bit, and that's what we record as the position of the atom. So this is an example of a platinum atom on a platinum surface. So we call this an add atom. The corrugation here that you can see is due to the arrangement of the platinum atoms in the surface. So because of this tunneling process, this is an extremely high resolution type of microscope. Okay, so in addition to imaging, probably one of the most cool aspects of this is you can use this tip to kind of nudge things around on the surface, which we call atom manipulation. So one way to think of this process is that if I tip a little bit closer in, I might start to form a partial bond, a chemical bond, between the atom on the tip and the atom on the surface. And you can use that bond essentially as a way to produce a force on the atom and move it around. And so what we might do is drag this atom a few nanometers over to the side. And then if we just retract the tip a little bit, we'll kind of stop perturbing the atom on the surface, and we've now moved it across the surface. We can go back to imaging mode. So these are some kind of fun examples. It's kind of trivial, but when you do sit at one of these microscopes, the first thing you want to do is make graffiti with atoms. And so the first time, I guess about 30 years ago now, by Don Eigler, he positioned xenon atoms on a nickel surface. And this was kind of the birth of the idea that you can create matter on the atomic scale that wouldn't exist naturally. So this process that I illustrated is kind of like toddler in the picture can do. So in particular, this sliding technique is kind of limited to making two-dimensional planar structures. Like I'm showing, all the examples here are actually 2D because they're just drawn by sliding something on a surface, whereas it blocks and put them on other blocks. So there are some techniques where you can use this method to build three-dimensional structures, but so far I've only been limited to looking at 2D. Okay, so I take one example from my group's research and kind of show how we can use this tool to learn something related to nanoscale computing. So efforts going on in my group. There's the photochemistry to the artificial leaf, like I showed you. We're starting to move into a quantum information sciences effort using two-dimensional materials to look at quantum bits. So for us, measuring a quantum bit, which might be an atom, is relatively easy. The hard part is kind of measuring the quantum properties of that atom. We're also looking at topological spin textures. So topology is this mathematical concept. And it turns out that there's magnetic textures that have this kind of topology associated with them. And this is an image of one of these kind of magnetic textures. And we have a kind of developing new ways to combine this microscopy with other methods. In particular, optics is one thing I'm interested in. And so I'll just highlight, it turns out Ohio State was selected to develop a national extreme ultraviolet laser facility called this. So this is kind of like a mini version of a national lab that's being set up in the chemistry building. And I'm part of this effort that's aimed at combining the STM with this extreme ultraviolet light to do new kinds of imaging. The example I wanted to highlight, though, is looking at magnetism in semiconductors. And so this is an STM image of 3 manganese atoms that we placed along a line. And we're interested in looking at the magnetism associated with those impurities, because this is kind of a way to combine logic and storage. So in our computers, we still have magnetic-based hard disks, particularly for large storage capacity. Those are separate from our computer chips, which perform the logic operations. That's because semiconductors generally are not magnetic. So magnetism is good for storage, but it's not so much used for logic. If we can make semiconductors, possibly new opportunities to combine those two. Okay, so let's look at a semiconductor surface. So the one we studied is called gallium arsenide. It's actually used in cell phones for high frequency applications. Part of the trick in getting this microscope to produce something useful is making a clean enough surface. And so one way to do that is you break a material, because then the surface that's revealed has never been exposed to air or any other kinds of contamination. And so the way we break this gallium arsenide crystal is we scribe a little notch there, and then we bring it into an ultra-high vacuum chamber, and then we press on that wafer until it just splits. And so this is an STM image of what this pristine surface looks like. So you can kind of see these white spots. Those are analogous to those little splotches that I showed you in the transistor channel. So this is kind of like that same kind of picture, but now where we're directly imaging these using the STM. If we wanted to introduce a magnetic atom, so we have kind of like a light bulb filament that can evaporate atoms onto the surface. And so this is an image of the same area, but now where these dark splotches that I've added onto the surface are individual manganese atoms. And one thing I really like about this image, when you do this kind of before and after imaging, it kind of reverse directions. And so let me highlight two places in this surface. And the top one has this dark spot, and we think this is a silicon impurity atom. The bottom one has this kind of, it looks like a Doctor Who Dalek. We have no idea what this defect is. Let's look what happens afterwards. So, and I'll flip back and forth. Okay, so these new spots here are the manganese atoms that I've added to the surface, but now this dark spot kind of looks like a bow tie shape. And if you look closely, you might notice this kind of faint arc here. It turns out that we've understood that kind of effect in the image as a change in the charge state of this atom. So the charge state and its appearance are changing. And in this case, it's because it's near this manganese atom that's on the surface. If we look at the Dalek, so here's the Dalek. Actually, if you look closely, you might notice a faint arc here. So that's also one of these ionization effects. But now when it turns out a manganese atom landed right on top of this thing. And so now it doesn't look like a Dalek anymore, and this arc actually disappears. And so I like this because it highlights that the properties of these defects depend not only on what the defect is, but also what's around it. And so it kind of opens up a vast phase space for exploring kind of all of the different processes that are going on inside our computer chips. Controlled way where we can actually implant the atom into the surface. And so this is called the substitution technique. And one way to think about this is that we've kind of taken an atom, it starts off in vacuum, we stick it onto a surface, so that's kind of like an intermediate state. And now we can also implant it into the surface where it strongly interacts with the material. And that's kind of like another distinct state. And so you imagine like the hydrogen atom. you can study it from vacuum all the way to being embedded in a material using this kind of process. And so this is an example of showing where we took these 3 manganese atoms. Right now they're sitting on top of the surface. And if you zap them with the STM tip, there's this kind of discontinuity in the current that's associated with the manganese implanting into the surface. Now we have a little that's associated with the manganese in the surface, so it looks different. And we also have this little new spot that's created. That's a gallium atom that got kicked out from the surface and is now sitting on top. So STM kind of can tell you, is very good at telling you that something's different. It can't tell you what it is though. So interestingly, we see that a manganese atom on top of the surface is very different than a manganese atom in the surface because they image completely differently. We can repeat this. So what we did was we nudged this manganese atom over next to the first one. And if you look here, you can also see a difference, which is not well understood. So again, STM is really good at telling you that things are different. So if I look at this little dumbbell shape versus this one, you can see that it's a little bit brighter here. So that's actually a real physical effect. It's not any kind of artifact or noise. It's due to the proximity of this atom, because everything else on the surface is exactly the same between the left image and the right image. So then we repeated this implantation, and now we have what we call a manganese dimer. And so here's another example. So this is, we call a tidal effect, because now there's 2 gallium atoms on top of the surface and 2 manganese atoms in the surface. The manganese are identical, but you can see that one of these dumbbells looks brighter than the other. And that's because the left one is closer to these 2 gallium atoms than the other one is. So even though they're both extremely close to the gallium, the effect on the order of about 4 angstroms, 4 nanometers closer, lets us distinguish them, even though they're otherwise identical. Okay, so I'm going to show one example of kind of some of the science that we use, automatically controlled the distance between one of the surface, and it turns out that those are charged. One of these manganese, we call them a manganese acceptor, that we implanted into the surface. And so the third capability of STM that I didn't have in my schematics was the fact that we can measure the energy states of atoms or molecules, and we call that spectroscopy. And so what we did in this series of experiments is we measured the energy states of this manganese atom as a function of distance to this other manganese atom that's on top of the surface. Okay, so this is a manganese in the surface. This is a manganese on top of the surface. So if you think about magnetism, it turns out that these are magnetic atoms. And so we can study the magnetic interaction between these atoms as a function of their distance. And so when you do this kind of spectroscopy mode, we see a pronounced peak in the spectrum, and that's associated with the manganese inside in the surface. And then we can just measure this peak energy as a function of distance to the manganese atom on top of the surface. And so all we're doing here is we're scooting this manganese a little bit closer in each time and remeasuring the spectrum on the center manganese right here. Okay, and you can see that this peak is systematically shifting toward, it's at the x-axis here is voltage, which you can think of as energy. So it's systematically shifting toward lower energy. So if we plot all these peak positions as a function of distance, you get a very nice demonstration of Coulomb's law for a point charge. So let's put those together here. So the black points here are essentially the shift in this peak as a function of distance between the manganese in the surface and the manganese on top of the surface. And you get a very characteristic 1/r fall off. And so what that's telling us is that the manganese on top of the surface is charged, and there's a Coulomb repulsion between the manganese in the surface and the manganese on top of the surface. And it turns out that this point charge you can realize in a few different types of systems. So for example, we've studied, sorry, it's gonna let me go back. Okay, we've studied 3 of these. I can't get them all to display on top of each other. So the blue points are gallium atoms on top of the surface. The black points are an arsenic vacancy, and the red points here are a manganese atom on top of the surface. And it turns out all of these are +1 charged. And so you can manipulate them like a point charge to create this Coulomb effect. Okay, so let me, now I'm going to kind of just wrap up by giving some motivation for what we might use this kind of technique for. So on the left here is an STM image thing called the single atom transistor. So this was made using STM to position atoms. There's one atom right here, that's this bright spot. And then this is an Australian group. What they did was they patterned electrodes, so source and drain electrodes in a transistor. And they could basically measure transport through this semiconductor channel, and it gets influenced by this single atom. So that's kind of the ultimate extension of conventional electronics. You can take transistors and make their functionality dependent on one atom. And the other, one other main thrust of this kind of work is quantum computing, which has of course been a huge topic in the news in the last few years. When I started in graduate school, quantum computing was just a proposal by Bruce Kane. So this was an idea that you take impurities in silicon and you can kind of turn on and off their interactions and produce quantum bits that way. Now, actually, this turns out not to be how quantum bits are made by Google that you might read in the New York Times. Those are made using superconducting circuits. But one advantage of this original proposal is that you can make transistors very small. And so if you wanted 1 million qubits, it's much more straightforward to do it using impurities in silicon than it is making 1 million tiny little superconducting circuits. Okay, so I'm going to finish by showing you the instrument, and then I'll show you some remote imaging.
Dr. Gupta?
Yeah.
On the previous slide, so I'm kind of curious then why has like Google and a lot of the current quantum computing work gone toward conducting bits instead of these?
It's mainly because it's extremely hard to position single atoms. And then also the atoms can be very sensitive to other atoms nearby. So it's kind of like a double-edged sword. You can make things very small, but then they can also be very sensitive to aspects of the environment controlling. So for example, in a single atom transistor, you know, I have the one atom that I positioned, but it's got all this other stuff nearby, which isn't controlled as well. In the case of the superconducting circuits, those are all kind of identical circuits. They're, you know, micron scale or so. So they're much more easy to precisely fabricate. And at least currently, they have higher performance for something like 50 qubits. So they're working well for a limited number of qubits, but the scalability of that approach is much more limited.
Okay, interesting. Thank you.
So you might have noticed in the news, you see like a picture of a quantum computer. It's essentially just a dilution refrigerator. And that's because, so the only thing they're really showing you is what's used to make the superconducting circuits cold. That's what people think of as a quantum computer right now. Okay, so I'm going to show you, this is an image of one of the microscopes that we built in my lab. This is our STM tip, and our surface here is this disc. This is probably a copper or a gold disc. And in this particular microscope, we added this capability to focus onto the tip. And so this is a lens that can then focus to this red spot here on the tip. And because I do need to go in a few minutes, let me just try to switch over to the remote imaging, just because I think it's always fun. And so let me show you how we do that. So it turns out Google Chrome has a very nice remote desktop client. And so these are some of the computers in my lab. The one that's going to control the STM that is running right now is okay, so this is a machine that's working in the physics research building. I'm here at my home in Grandview. And actually it's imaging a surface right now. So you can see these bright spots. Those are some of these individual atomic scale clusters on a gallium arsenide surface. So actually the same one I showed you the research results on. This red line here shows the progress of the STM tip And so let's see, this image is 500 angstroms. So it's 50 nanometers by 50 nanometers. Let me go ahead and stop that and zoom in a lot more. So let's go, instead of 50 nanometers, let's go to 10 nanometers. So 100 angstroms. Okay, so now we can kind of see these individual atoms much more clearly. And in fact, just to make things a little simpler, I'm going to assign the bias voltage. And one of the things we spend a lot of time is studying kind of, does the voltage matter in terms of our imaging? And let me also, because I'm less patient than my PhD student, let me speed this up a little bit. Okay, so now this is a 10 nanometer square image, and that's about the scale where you can start to see kind of individual atoms very clearly in the images. And we'll try to see if there's something that I can identify. So we have kind of a bunch of these spots here. Probably the only one that looks familiar to me is this one right here. So if you remember the individual gallium or manganese atoms on the surface, kind of look like a bullseye shape. They had like a bright center and a dark ring around them. So I think that's one of these atoms on top of the surface next to this bright blob, which is probably like another molecule, a contaminant on the surface. There's another thing you can notice from the images is if there's this kind of a column-like pattern. So I'm going to draw my mouse along one of the columns like this. They're running straight up and down in the image. That's actually the gallium and the arsenic rows in the gallium arsenide semiconductor. So we're imaging the atoms in the surface as well as atoms on top of the surface. And this is happening right now in PRB, but I'm able to control it remotely. So one of the things we do, is particularly during the COVID shutdown, is we kind of get the sample ready in the lab and then do a lot of our imaging remotely. And it turns out actually the microscope works a little bit better that way sometimes, because we're not kind of present in the lab making noise or eating potato chips and so on. It's very sensitive to vibrations and acoustic noise. So instead we kind of sit outside in our office or at home and image remotely, but only come into the lab to kind of prepare surfaces or change samples or things like that. So I'll just leave this up, and I'm happy to take other questions that people have.
I can read out anything in the chat if someone would rather type there.
I'm just going to fiddle around with this a little bit while people are thinking.
I'm curious, how much of a hassle was it to get this working remotely?
Oh, Google Chrome does most of it? Well, that's why. But I hope I didn't mess anything up right now. But this is a good illustration of the dangers of remote imaging. So you know, the control software for the STM is not very sophisticated. So it's easy to kind of cause it to freeze or crash, which often will cause the tip to crash. And fortunately, I didn't do that this time, because otherwise Rebecca would be very upset with me.
What does it mean
actually, this
to
is a nice
crash
image.
the tip?
What that means is that you lightly touch the tip into the surface. And what that does is it nudges the atoms on the tip into a kind of a random configuration. Sometimes it's better, and we actually do it intentionally. But if we have a good tip, then we want to keep it. And then we get very upset if it happens when we don't want it to happen. So what I did now is zoom out a little bit. So this is an 800 angstrom image. So 80 nanometers by 80 nanometers. And you can kind of see a variety of these little specks. There's these kind of bright spots here, which we think are actually clusters of gallium. There's these dark spots, which Rebecca is studying iron. So we kind of did some initial studies looking at manganese and gallium arsenide. And this is a study of iron, which has a different configuration of electrons in its D shell. And so it has different magnetic properties. And so Rebecca is trying to kind of extend the work we did, but now looking at a new kind of magnetic atom. So I'm going to and it's my computer's a little laggy running a remote desktop and Zoom at the same time. It's usually more responsive, but so let's zoom in somewhere where there might be something interesting happening. So let's go there. And then now it's so
seems to have fixed itself.
sorry, can you say that again?
And your mic was making some weird noises for a second there, but it seems to have fixed itself.
Okay, thank you. Yeah, it's probably my computer's struggling a little bit. So one of the things we spend an inordinate amount of time in is kind of randomly smudging the atoms on the tip so that they image better. Sometimes if they're kind of in a strange configuration, things will kind of look doubled or tripled. So I think this is an example, because if you notice, there's these spots here, which we think are these atoms on top of the surface, but they don't just look like little circles. They're kind of smudged into like almost like an L shape. And you can see that a few of them look exactly. That's an indication that it might be a smudging of atoms on the tip rather than just a single acting out more than the others. And so one of the things that we might typically do is kind of do a controlled touch to the surface to smudge those atoms around. And by chance, you know, about half the time it gets better and the other half the time it gets worse. And so probably the single most time consuming aspect is kind of preparing the surface and the tip to really get very nice images. Let's zoom out again. Well, I'm happy if no one has other further questions, I probably should run, but please feel free to send me an email if you are interested and want to learn more. My name.n is Gupta.208, and you can also, of course, find me on our webpage. But yeah, any last questions?
I'm not seeing anything in the chat, so I think we're probably good.
Okay, well, take care, everyone. I hope the semester has started off well, and hopefully it will stay going well.
Thank you very much.
All right.
Have a good evening.
You too. Bye, everyone.
All right, then. Thanks for coming, everyone. Normally, our meetings would run till 7 p.m. and in the future, hopefully they will. But, you know, quarantine and COVID have made everything a little bit more complicated. And sometimes during the semester, we also have shorter meetings sometimes for whatever reason. That being said, I used to work for Dr. Gupta. So if you have any questions about how the process works, I might be able to answer a few of those. But I posted his email in the chat. Of course, you'll probably get a much more thorough answer if you ask him directly or one of his research group members. So stick around for a few moments to answer anything like that. But otherwise, thank you everyone for coming, and I hope you have a good evening.